Good afternoon. My name is Stefan Szyniszewski, and I'm happy to present you my research plan. Of course, my research plan is coming from my PhD dissertation, and this is the starting point in my research career. Progressive collapse of buildings resulting from abnormal loadings. Why is it important? What's our motivation? These problems received very broad attention after September 11 and the World Trade Center collapse, because people realized that all buildings are susceptible. Every building is vulnerable to such abnormal loadings, and it can collapse and people can die. A very good example of the current state of design and practice is the collapse of Murrah Federal Building in 1995. Usually the buildings are designed to stand. So you build a building, like Chris said, you walk away, the building is there. No one is considering the abnormal loadings or the disasters in the design process. So when such abnormal loading like an explosion happens, this is what we saw in 1995. There is an explosive going off. We see the blast pressure entering the building, raising the slabs, and they were lacking reinforcement at the top because it's not the usual action. Usually the slabs, they don't bend upwards, so they cracked. And once the pressure wave passed by, they collapse. The cracked hinges close to the supports are unable to support the slabs anymore. The slabs are damaged. They fall down. We see the columns. They lose the lateral support, so they buckle. We have 3-4 stories of unsupported columns, and they are not designed for such loadings. And the building collapses. People die. We have news coverage. So these are the things we want to avoid. And when we state the problem, we can say that progressive collapse is a catastrophic structural failure that ensues from local structural damage. So we damage a structure very locally. We do little damage. We destroy 1 or 2 columns, and the result is disproportionate to it. The other main difference is the time scales. The initiating damage happens over milliseconds, and then we have the global damage happening over seconds in a different time scale. And what we have now, after many years of research in this area, is that we still have absence of simplified yet realistic tools to evaluate if the building, how the building is going to respond to such a disaster, such tragedies. What is the research I propose? I have a unique expertise because my master program, I received my master program in mechanical and civil engineering. So part of my training was done in Germany at the WTH Aachen, and part in civil engineering. So I have this unique knowledge of mechanics, which most of the civil engineers don't have. So I use the car crash simulation tools, which are more advanced than civil engineering tools. The automotive industry uses it to simulate car crash, BMW, Ford, all these companies, and they are based on very sound physics, but they are very difficult to use. You need teams of people who can use it. So I use these tools to simulate the progressive collapse of buildings. This is a steel frame, and 2 columns are instantaneously removed, and we see how the building responds to it. We see the simulation, and when people question it, they say, oh, it's nice animation. How do I know it's true? How do I know it works? So this is the whole art of it. You can give the same software package to someone who knows what he does and to someone who doesn't, and you will see different results. So what I did a validation test with the experimental data. So this is LRFD buckling load curve, and this curve is derived experimentally. People in 80s tested hundreds of columns. They came up with curve fit. The dots represent the results I obtained in simulations. So basically applying compression to a single column and recording the buckling load. We see very good agreement. I had to use large strain models, large deformation models, introduce random imperfections to the shape of the columns and the assembly accuracy using the codes. So this required a lot of work, but at the end we can get to the physical reality. So this is an example of a simulation when one corner column is removed, and usually these corner regions are the most susceptible ones, and we see that the building survived. So we performed a virtual experiment. It doesn't cost us anything. We just use software. We know what we do, and we see what would happen if we had an explosion in the corner of the building. And this is an animation showing the structural response when we remove two columns, and we can see that the building would collapse. This is an illustrative example where all the connections are very strong. So they are like welded connections, and it shows that very strong connections are not always the best solution. This is what is advocated right now in the codes as a prescriptive measure, that we tie everything together, and this makes the building safer and stronger. But if we have very large explosion, the collapsing elements will pull the surrounding structure down, and instead of limiting the collapse, we basically propagate it throughout the whole building. So there is no one simple answer to this problem. That's why we need more comprehensive and physics-based simulations. And then how we test it, I came up with the free fall test. So basically when buildings fall down, they cannot fall faster than free fall. When we go to Italy, to the Pisa Tower, we drop a stone. When building collapses, it will not fall faster than that. It can fall only slower, because we have columns which crash, which stop the motion, damp the motion. So to achieve this effect, what people do in civil engineering with the loads, they say there is pressure load on the slab, on the deck, 5 psi. And where does the load come from? It comes from the desks, from the paper, from whatever we have. But these objects, they all have mass. So by applying loads as pressure loads, we neglect the inertia effects. We neglect that they have mass. If we do this, these are the curves we will obtain from the simulations. They fall much faster than the free fall curve. If we apply the load as a gravity, so basically I would increase the mass of the deck such that the weight of the deck is same as the loads we have. So basically lumping all the desks, all the seats, all the human loads into the mass of the slab, we will preserve the inertia property of this object. So when we perform the simulation, we see that it follows the free fall curve, then it plateaus when the three columns buckle. Structure tries to prevent the collapse, tries to absorb it. It's overwhelmed, and the building continues to collapse. So it's important to do these physics-based simulations because they give us the understanding of what we can do to prevent it. It's a good starting point to do the general disaster management simulations, because I can take the same model and apply fire on the whole story, or hit it with a huge truck, or simulate a hurricane. So this is a model which can be used to simulate the whole array of different events. So I think there is a potential to develop it, to go from steel structures to reinforced concrete structures, and it seems like engineers are pretty much satisfied with the level of design, the static design of the structures, but there is a lot of questions in hazard mitigation. If we have a strong hurricane, if we have an earthquake, if we have an explosion, what's the response going to be? So I see a big potential of developing this research in the future. That's all what I want to say you, and I leave the floor open to questions.